Hi, today we are going to look at database reasoning over text from Facebook AI. It is an interesting paper and stands apart from other papers where most of the NLP publications are improving or around transformer-based architectures. This one is more towards querying over unstructured, non-schema-based NLP databases at scale. Previously, we have seen many approaches to query over a large datasets in transformers like Longformer, Big Bird, and others using random attention. Actually, we can actually see the Longformer and Big Bird papers because they both are most similar only. So in the Longformer and Big Bird, if you can see, both of them are using any kind of local or global attention where the input is m into m, where m is our encoded sequences, and what we know that in attention there is a quadratic complexity of m squares whenever we are using self attention mechanism. So what this long form of big bird does, it has a local or global attention, where in the local attention our each element would be multiplied only by local elements only, and in the global it would be mapping to the all global elements, but both of them does provides an issue, and this is the best for if we want to do attention mechanism in images. But if we are considering for databases, it is not ideal, as they are we if we are querying for any element over the data, that some of the values will be blank, and for example, if we are querying over some how many items are there for each one, and we will be getting uncertain data in terms of that also, because our query would not be focusing more on all the elements on the database. So that's why we went using any sort of database for our attention mechanism, where mostly these papers try to solve around that. So let's see the paper. If you like this content and would want to support it, please hit like button. Also, for regular updates, you can subscribe to this channel or can follow me on social media, which will be mentioned in the description. Any suggestions, opinions, or clarification will be best expressed in comment section. So let's go over the abstract first. Let me take the highlighter. Okay. So neural models has shown impressive performance gains in answering queries from natural language text. However, existing works are unable to support database queries such as list, count of female athletes who were born in 20th century, which requires reasoning over sets of relevant facts with operations such as join, filtering, and aggregation. Okay, assume you have to create a database for personal voice assistant. How do we create a schema for efficient and optimal storage and query? So this is the problem, and as we know, most of our data is unstructured, and to efficiently query this unstructured and these types of data, it is still a research task which these papers try to solve. We show that while state-of-the-art transformer models perform very well for small databases, they exhibit limitations in processing noisy data, numerical operations, and queries that aggregate facts. So here also they have mentioned about the transformer architecture in the databases. Now, as we all know, transformers are the best in NLP queries. However, what they lack is quadratic space complexity that we discussed in multi-head attention. Actually, for that, you can actually see the Perceiver IO paper which I have released, and where actually I have provided a more context on that problem, which Perceiver IO also solves. but that is also not created for database. So I don't think so that will be also best for this thing. Apart from that, this is the thing that we have actually understand. Now let's go over it. We propose a modular architecture to answer these database style queries over multiple spans from text and aggregating this at scale. We evaluate the architecture using WIKINLDB over novel dataset for exploring such queries. Our architecture scales to database containing thousands of facts, whereas contemporary models are limited by how many facts can be encoded in direct comparison on small databases. Now, this problem which it mostly relates to is the question answering problem, where there would be a paragraph P, there will be some paragraph of text. We can think of it as 200 or 300 words in a paragraph P, and there will be a query Q for that the question would be there, and the values would be in the paragraph only. This would be the input sequences, and using the input sequences we would have to take the query also and the paragraph also to provide the output. This actually for this traditionally we are using square dataset, the Stanford question answer dataset that actually contains a lot more information around that, but they are using WIKINLDB dataset, which is a modification to squared one, and we will be checking that out also. And they have also provided the architecture where it would have to find results to queries from over thousands of documents of sentences over the database. So let's check the WIKINLDB dataset first. So here you can check it out, where we can see for WIKINLDB the database is of different sizes and lengths, and it contains the dev text and train JSON for every set of datasets. Now let's check all the what is present on the dataset also. Here I have just taken a sample one where we can actually there will be multiple sentences per information, and where we would be and there will be many sections around that also. Now let's check it out. Now for right now we can focus on facts, past targets, parses, and valid hypothesis. Let me zoom it out. Okay, so the facts, the past targets, the parses, and the valid hypothesis. So what are the facts? Facts are just an information which is stored in the databases. It is actually contains the raw schemaless information that we will get the information later. The past targets. Now we can see that sentence, the wicked world is a play written by W.S. Gilbert. For that, the past targets are the targets which have been filtered out from facts having information. These are the two words that actually contains the information in the sentences. Now parses. Now this parses provide a unique IDs to the targets. You can see for the IDs differentiate based on the types, and also it's supposed the date time. For this we don't have any date time, but you can see the IDs. Let me get the another data sets. Yes. So here you can see the date, where it also encodes the date in terms of an ID per se. And then there are the valid hypothesis. So valid hypothesis provides the context relationship between the parses. So here you can see the wicked world instance of and play theater. Here is there's some relationship that they are providing in terms of these sentences, where we will be checking it out. And I can understand that this will be some kind of complicated. We will be going over all of this later on. But here's the basic idea of the database that it provides. There is a tool that they have also provided. Based on that also, we can actually modify our knowledge graph databases to this kind of database where the encoding would be a lot more simpler for our architecture. So let's understand how does it does that. So let's go over the facts. To automate the generation of questions and answers, sentences must be grounded in Wikidata identifiers. One approach to generate facts would be to use templates or collect them through grounded information expression datasets such as T-Rex. We use verbalization of knowledge graphs, triplets that are synthesized through a sequence-to-sequence model. Concretely, we use generated sentences from Kelm which are not grounded with Wikidata IDs and generate a post hoc mapping back to Wikidata. So what they have provided is that for facts, they are actually using a sequence-to-sequence model like Kim, which can convert the knowledge graph data to regular sentences, and then it get mapped with Wikidata IDs to create a relationship. For context, this is actually a good example of the Kim dataset that it provides. Using the knowledge graph, it actually converts it to a sentences, which actually contains the facts of the information this paper also tries to solve. Suppose we have a sentence in the database. Queen Victoria is the queen of United Kingdom. So if the Queen Victoria is A, the Queen is B, and United Kingdom is C, the relationship would be A into B into C. Now, if in the database there will be another sentence like Queen Victoria died in 1901. So again, the Queen Victoria should be mapped with A, and that can be the D, and 1901 can be a mapping of E. So using this mapping actually get some idea in the templates. We have a template of Wikipedia, which we can use to understand the context in the database. And the authors actually has also said the architecture code where we can incorporate our database to be converted into facts and passes away what they are using. Now this fact can be single fact. For example, a sentence containing a single fact, Gustavo likes espresso, or multiple facts such as Robertson Howard, who attended the University of Virginia, is buried in a congressional cemetery. So basically, the Gustavo likes espresso is a basically single fact that actually provides that Gustavo likes espresso. In another sentence, the Robertson Howard, who attended the University of Virginia, is also buried under congressional cemetery. So this provides a two context fact in the values which can be interlinked. So let's understand the architecture now, how to query the data. Here, this is basically the idea of the architecture that they have provided. There will be a range of facts, like John works at Shell, Sarah is a doctor, and Sarah married to John. There will be a query also in the database that actually is the question that we want a value from the data facts table. There will be a support set generator. The support set actually contains the minimum subset of sentences from the database needed to generate one single operand to go to the next step, which is the neural SPJ. This neural SPJ, which actually means the select project join operator, outputs a intermediate representation of the answer that can be generated from the support set. Now, after neural SPJ, it can understand that if the values need to be aggregated or it is a boolean or any other values, and based on that the aggregation model will be working. It will then aggregate the neural SPJ values and it can provide a numerical values. That's what the query wants. We will be going in each of the every section and we will understand that how it works. Now we have actually gone over the facts, so let's go over the query. A query is just a simple sentence that actually we provide to the architecture from what we want the values. Now these queries can be of different types that they have provided. First, a set queries are queries that return a list of spans such as entries from the facts. Then there can be Boolean queries that returns a true or false answer. There can be aggregation queries that requires computation over answer sets of operators such as count, mean, and max. Like they provided the example. How many people work for Yale Law School? There is a fourth query type of query also, which provides the join queries that requires the combination of the two or more facts to produce each value. Honestly, there would be many more types of query for reasoning over the text. However, I can understand, and these four would be easily cover most of the cases. Now, let's go over the support set generator. A support set contains the minimal subset of sentences from the database needed to generate one single operand for the aggregation module by the SPJ operator. For example, for queries that are answered by a single sentence, example, who is Cyril's husband? The support set containing a single fact should be written, example, Cyril is Nicholas' spouse. The output of the support set generator is a set of support sets, each of which is fed independently to a downstream SPJ module. So based on the queries and facts, it maps the encoding parts of the queries to the facts to provide the subsets from the databases. So basically, support set generator provides the minimal support values from the facts that contains the context of the queries that it is providing. Basically, it encodes the support, the facts values and the queries using a bioencoder, and then it understands which of the values would be the minimum support set to provided. For example, they have actually provided the TF-IDF idea in TF-IDF where each of the there will be each of the facts table on one dimension, and there will be values of queries on another dimension, and based on the queries and facts, we can provide the importance of the facts table, and based on that we can provide which of the document is actually important for support set generator of the facts for the queries. But this actually doesn't scale well, and also it doesn't provide the context if there are sentences on there's values on multiple sentences. For that, actually they are using a bioencoder transformer to encode the facts over the queries and to generate scores for that. Here let's take an example for the bioencoder. So in this case, if we provide multiple sentences for facts of facts A and B, it will be pre-computed in a pre-training model like BERT pool, and then a uniform encoding will be done for each sentences, and based on that we can actually compute the quotient similarity between the sentences also and between the queries also, if that will be provided to this same bioencoder. And based on that we can understand which sentences are most similar to the queries and can provide the context around that. This also helps us if the sentences are far away also in the database. Even though it will be far away, it will be having the same encoding and it will be scalable enough also. Compared to that, if you use cross encoder, it will be providing the better results. But if you understand all the values, it will be providing the classifier, but it won't be scalable enough. As for two sentences, it will provide the similarities of the scores, but if there will be another sentence, then all the sentences would be again trained to provide the classifier scores. Despite here, we are getting an encoder for a sentence, which if there will be another sentence also, we can actually encode them in the same architecture, and we can compute the quotient similarity based on the encodings. Now let's go over the neural SPJ model. Now we have actually understood for neural SPJ model. Now support set is been done. Based on that, the neural it will be provided the values to the neural SPJ, where the operator would be returning three types of output. If there is some context around the support sets, then it will provide the values from the support sets that actually match with the queries. If the support sets are inefficient to answer the question, the operator should return null or no output. For queries that requires short chain of reasoning also, it actually maps with another subset also, another support set also, and then it can provide the values. If not, the single support set also from single support set also it provides the values. It also provides the token also if we want to go to the aggregation model to aggregate multiple supports, multiple neural SPJ values to provide a numerical values around the queries. Let's understand more on neural SPJ. The SPJ model is trained as a sequence-to-sequence model to generate the intermediate results from a support set and a given query. All facts in the support set are concatenated with the query before being input to a transformer model. So this is also a sequence-to-sequence model, which actually provides a machine-readable understanding of. So this is also a sequence-to-sequence model, which actually encodes the sentences to a machine-readable format, which actually extracts the values from the support sets. Here they have provided the example also, what will be provided to the neural SPJ. We will be providing the queries and the support set, It is similar to what we have seen on question answering dataset also, where we were providing the paragraph and the questions also, and based on that we will be providing the values. It is similar to that only. In addition to that, it also contains a tokenizer also, which actually just provides a context, as in we have to aggregate these values or you have to just provide the values as it is through in the queries part. So let's understand the aggregation model. It is simplest of all. Basically, based on the token that is provided by neural SPJ. Let me go over the chart. Yes, from the neural SPJ there will be a token, as in is if the aggregation model has to be written or not. And based on that, the aggregation model will be done, and it will be merging. If the aggregation model should be done, it will be extracting the values from the neural SPJ, and based on that, it will be computing the count min max values from that. Here we can also see the final metric that they have provided. Here we can see that the neural SPJ does perform a better compared to the long form or FID. So this is the code the Facebook research has provided. In this, they have provided the dataset construction. Using that, we can actually create our own WIKINLDB dataset like thing, and the modeling in SSG is there. I have actually replicated the same in a Colab for a quick reproducibility. For a simple benchmark, they have provided the thing. It actually uses the SBIRD on the package for the bioencoders and other things. And for a simple basic neural DB also, it takes a lot of time. But for evaluation, we can see the final values of what it provides for the WIKINLDB. As you can see, the min max accuracy, the set, boolean, and the count values are there, and it's quite good according to what it has provided. I will be saying this notebook also in the description below, which we can actually check it out. And that's it for this paper. This was an interesting paper, as this was focused mostly on the database understanding and how to query an unstructured database. I will be looking more towards it. And if you have any such query suggestions or any other thing, please mention in the comments below. And take care of yourselves. Thanks. Bye.